Welcome back. So now we'll continue the discussion on this statistical data analysis. Obviously, we have talked about this different um, direct method of beans, and the statistical ways of. So there, the major aspect of it is this a different kind of probability or probabilistic distribution uh, of the wind velocity. So once you know this probability distribution function, so what it allows that you can estimate the. So we have talked about. Earlier we have talked about this um, Rayleigh distribution, which we have seen, which is represented like, which is a special case of Weibull function u by square exponential minus pi by 4 u by u prime square, and my cumulative distribution function would be 1 minus exponential minus pi by 4 u by u square. So this is what we have seen. This is a kind of an special case of. Then we have this Weibull distribution, that also. So the probability distribution function of that based on two parameter. One is the k and then the k minus 1 exponential minus u by c to the power k. So this would be 1 minus exponential u by c to the power k. So these are the distribution. Then we have also looked at normal or Gaussian distribution. Okay, so this is a different kind of distribution that we have seen, which are there. So what happens is that using this Weibull distribution function, so we can find out the average velocity, which is u bar c gamma of 1 plus 1 by k, and gamma of x, which is gamma function, is 0 to infinity t to the power minus dt. So gamma function one can estimate like root over 2 pi x minus 1 e to the power minus x 1 by 12x minus 139 840 x cube, so on. Similarly, for this Weibull distribution, sigma u square is u square gamma 1 plus 2 by k plus 1 by gamma square 1 plus 2 by k. So minus 1. So this also you can find out. So it's not quite straightforward to get C and K in terms of U bar or sigma U. However, there are some number of approximation that one can use, because the factor that is going to play an important role in this estimation is C and K. There are some analytical or empirical, let's say for K less than 10, greater than equals to 1. So the approximation could be K equals to sigma U by U bar minus 1.086. Then what one can get, U bar C equals to U bar by gamma 1 plus 1 by K. But obviously still you need to evaluate the gamma function here. Gamma function. That one has to evaluate that. Now, some other empirical formula. So this is the first one. This was by, again, Justus in 1978. Then again, some empirical relation. This was by Lysen. Here, C by U bar 0.568 plus 0.433 divided by K to the power minus 1 by K. Okay. Then one can use some kind of a graphical, which is log plot. Okay. This was provided by Rodgi and Nelson in 1994. So this is essentially it's a graphical based approach. So where you use this to get this estimation of directly that U cube mean, which was U cube P of U du. So the shape factor kappa is there. Then, for example, energy pattern Ke, which is K is U cube bar by U bar cube, which is gamma 1 plus C by K 1 by K. This allows some calculation to estimate all these things, to have these calculations. Now, what you can have extreme wind speed as well. So the primary meteorological factor in evaluating a prospective wind turbine site is the mean wind speed. And another important consideration is the anticipated extreme wind speed. So that means you have mean wind speed, then you have anticipated extreme wind speed. This is the highest wind speed expected over some relatively longer period of time. Extreme wind speed are kind of some concern for design purposes, since the turbine must be designed in order to withstand such extreme wind speed. Now, these are typically described in terms of recurrence. Specifically, an extreme wind is the value of highest wind speed, which is averaged over some approximated time interval with an annual probability of occurrence of 1 by n years. For example, the highest 10-minute average wind with 50-year recurrence period would have a probability of occurrence of. Actually, determination of extreme wind speeds by actual measurement is quite difficult since it would require measurements over a long period of time. It is possible to estimate extreme wind speed, however, by using extremes over shorter period of time together with a statistical model. Okay. So the most common statistical model for estimating extreme wind speed is the suitable statistical model is the Gumbel distribution. So this is what is used to estimate extreme wind speed. So the distribution of this P of UE 1 by beta exponential minus UE minus mu divided by beta exponential of minus exponential minus UE minus mu by beta. Here U is the extreme wind over some time period. Obviously, it has to be satisfactory. Beta is sigma e root 6 by pi. Mu u is ue minus 0.577 beta. And ue bar is mean of a set of extreme values, and sigma e is standard deviation of the set. Standard deviation of the set. Okay. We can have the cumulative density function of that, which is exponential of minus exponential of ue minus. Gumbel distribution also looks similar if this is my u, this is p of u, this also goes again. So this has a similar tendency of or similar kind of nature that one see in Gaussian distribution. So it has the so now what we get now, we can get all the wind turbine energy production estimate. So wind turbine energy production estimates. So this is all, let's say, using statistical techniques or method. So what you have is that for a given resume of probability density function, PU, so what we can get the average wind turbine power, that is P bar W. We can estimate PWU, P of U, DU. So this PW bar, which is average wind turbine power, can also be used to calculate a related performance parameter, called the capacity factor. The capacity factor of a wind turbine at a given site is the ratio of the energy actually produced by the turbine. So this is capacity factor, which is actually produced by the turbine to the total energy that could have been produced if machine run at its rated power. That means PR. So PR is rated power. That means this is how we estimate the capacity factor. So obviously also one can determine the turbine power, curve, using the turbine power curve, wind power coefficient CP. So what happens is that once we have CP as a power coefficient, so we have PWU would be up rho A CP eta UQ. Here eta is drive train efficiency, which is essentially the generator power to rotor power. Okay. And A density, these are all known. So then what we can get is that CP is rotor power to power in the wind. So P rotor up rho UQ. So typically CP is also a function of tip speed ratio. So the tip speed ratio, which is lambda, is blade tip speed to wind speed, which is omega r by u. So omega is the angular velocity, which is in radian per second, and r is the radius of the wind rotor. So if we assume a constant value for drive efficiency, then what we can write, assume constant value for eta. What we write is that up rho pi r square eta 0 to P of lambda u cube pu du. Now using this, one can estimate the power and all these things using statistical analysis. So one can have some idealized machine productivity calculation. Here we use Rayleigh distribution to make our life bit simpler. So in idealized wind turbine, so since it is idealized, so that means no loss, the CP would be 16 by 27 as per Bayes limit. This will again, talk in details when we'll talk about the momentum theory and things like that. So this is the maximum theoretical possible power coefficient that can have. Then what we can estimate, so we know the Rayleigh distribution, so we can estimate this PW bar is half rho pi r square eta 0 to infinity Cp lambda u cube 2u by uc square exponential minus u by uc square du. Uc is characteristics wind velocity, which is 2u bar by root pi. Now for an ideal machine, eta equals to 1 and Cp is equals to Cp Bayes limit, which is 16 by 27. So what we have, PW bar is up rho pi r square uc cube Cp Bayes u by uc cube u by uc square du by uc. Now one can now normalize the wind speed by defining dimensional wind speed. Some, let's say, dimensionless wind speed, which is x u by uc. Then this integral becomes PW half rho pi r square uc cube 0 to infinity x cube 2x exponential minus x square dx. So what you can see that wind machine constants have been removed. The integral now can be evaluated over all wind speed, and this value would be, so if we integrate this, this would be c by 4 into root pi. So what we have now, PW is half rho pi r square uc cube 16 by 27 3 by 4 root pi. Now we can use the diameter d, then we can little bit simplify it, is rho by 2/3 d square into cube. So this is what you can see. One can calculate the average productions and things like that using this kind of. So once the probability distribution is known, then you can estimate this, and then using the annual power productions for this thing. Also, you can do some productivity calculation for real wind turbine. So this is use Weibull distribution. So here what we have, the PW bar would be 0 to infinity, PWU, PU, DU. So what we get using cumulative distribution function, so we can write PWU D of FU. And for Weibull distribution, f of u is 1 minus exponential u by c to the power k. So once we replace these things, so what we can get is j equals to 1 to nb exponential ug minus 1 c to the power k minus exponential uj by c to the power k pw uj minus 1 plus uj by 2. So this is some kind, I mean, the statistical methods you can see that has the similar expression that we have. So these are the kind of ways that one can estimate this. So the final thing that we would like to touch is that regional wind resource assessment. Okay. So what has been observed is that the major barrier for development in many regions of the world is a lack of reliable and detailed wind resource data. So one of the first steps required for regional wind is an estimate of the available wind resource. So there are many methods which one can use to estimate that. So some methods will just, one is the Falk-Rohr method, measurements only. Then you can measure, correlate, then predict. You can use global database. You can use wind atlas methodology. You can have site database modeling, then mesoscale modeling, combined meso or microscale modeling. So these are a different way one can do the resource assessment for regional resource assessment, because these are again to have, since there is a lack of reliable and detailed wind resource data, so regional wind database assessment is very um, important. One can estimate using different ways to get some idea about all these things. So what we have done is that we looked at the atmospheric boundary layer, how the lapse rate is happening, and then we have also at this different statistical methods and distribution function, how one can use those to estimate the wind power and all these things. I mean, the major key idea here is that all these different things are there available in nature, because nature surface is not smooth. There would be terrain, there would be some roughness, and all this is going to have some impact on the wind velocity profile, or one can say that there is the effect of the atmospheric boundary layer, and then that's going to affect your wind shear, and wind shear is going to be key design parameter for turbine. So that will see how wind shear, when they affect and all this, when you go detailed discussion on these turbine parameters and all these things. So with that, you have a fairly good of idea how, what are the resource of the wind motions, how that is happening, how that is impacting these things. Now we can move to discussion about power calculations and all this. Okay, so that we'll do in the next.